Well, it's everybody's favorite networking topic, subnetting. Actually, I really do hope it is your favorite when it's said and done because when you get it, it's really neat. It's like figuring out a puzzle every single time. So we're going to look at subnetting over the next few nuggets. First thing that we're going to do here is first off define it. What is subnetting and explain where I would use this skill. And then we're going to look at the first style of subnetting, and that is subnetting based on network requirements. All right, I'm going to jump right into a network scenario and use it to describe subnetting. So in the last nugget, we talked about IP addressing fundamentals, and we saw that IPv4 has three default classes of addresses that we use on our networks today, class A, B, and C. And based on the class of address that it is, you can determine what the default subnet mask is. Now, we saw in the last nugget that you can look at the first octet of the address and determine what class of address it is. So if we have, for example, I'm writing it now, 128 through 191, we know it's a class B address, while 192 through 223 in the first octet of the IP address will be a class C. So if somebody threw out a 150.5.1.9, I would immediately look at that and go, aha! First octet, this is a class B network by default, so its default subnet mask is 255.255.0.0, which I know very few people will actually use a default subnet mask because it gives us way too many hosts available per network, and most of the time we want more networks. We want to be able to break that down. Well, that's what subnetting is all about, is it's saying, well, you know what, these class full address masks, or classful subnet masks, I should say, are great and all, but they're not really useful. I want to be able to customize this subnet mask based on my network requirements, even going beyond these big boundaries. You know, going from 255 to 000, or I should say moving from a class A to a class B, is a big change. I mean, you're going from 16 million host addresses available here, down to 65,000 some host addresses, down to 254. Okay, come on, our networks need a little more flexibility than that. So that's where our custom subnet masking comes in, right? So let's see, where do I go from here? Let's talk about binary conversion. So let me wipe this out for a moment. Converting to binary becomes one of the core skills that we need because that's how our computers work with IP addressing. That's how our computers see subnet masks is in the binary. We see the decimal numbers. So in order to work with binary, we need to kind of go into a, well, I'll just use my normal example, go into a shop that Rico invented. Rico is a brilliant inventor who invented indestructible bricks, meaning, construction bricks that you build walls with and things like that. These are lightweight, inexpensive, indestructible bricks. And Rico, the owner, while being a brilliant inventor, was not a big businessman or figuring out a lot of base systems, if you will. So he just made a giant pile of 10,000 bricks in his store, hired Bob, the floating assistant, to run around and pick up bricks as necessary. So the first customer would come to the store and say, hey, I want 200 bricks. And Rico would yell to Bob, hey, Bob, get 200 bricks. And he'd go, fly around, grab these bricks and deliver to them to the customer. Well, you can imagine that would take some time, and so as the customers began lining up, getting smaller and smaller as they went, yelling out, I want 150 bricks. I want, this guy in the back's like, I want 5 bricks. They're yelling out these values. Well, it's killing Bob. His sweat's pouring off of his head. He can't keep up, and soon collapses. Rico closes the store and says, Bob, what can we do? Bob says, we need to palletize these bricks. We can't just have a pile of bricks. So I'm going to create some pallets for you, Rico. We'll have a pallet of 128 bricks, a pallet of 64 bricks, a pallet of 32 bricks. I know some of you are like, I know where you're going with this. Pallet of 16 bricks, 8, 4, 2, and 1. I guess you don't really need a pallet for one. You just have a brick. So you got all these different pallets of bricks, and tell you what, Rico, I'm going to give you some flags, and so whenever a customer comes and asks for some bricks, you just put the flags in the pallets that they need, and I'll use my handy dandy forklift that we just bought to go wheel these pallets out to the customer. So ching, 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 the door opens back up on the shop, and the guy's still sitting there waiting for 200 bricks. Well, Rico simply turns around and goes, ching, ching, I'm going to put a flag in 128, so he does some quick max. Now, Rico can do this in his head. I cannot. 10, 9. So, by the way, you never get a calculator on Cisco exams. So, longhand subtraction sometimes is the method. So, we need another flag in 64, right? So, I'll do 8 left over, so none here, none here, none here. Okay, there's our 8, and that will give us 0. So this ends up is where Bob wheels those out. Happy customer, much speedier, right? Well, the computers work the same way, but instead of flags and pallets of bricks, the flags really equate to ones, and these are all numbers in the power of 2. See, this is those 8 binary values are really the powers of 2. So when I look at the number 200, the binary equivalent of it is 11001000. That is the binary equivalent. Now, these are all powers of 2, so the one on the far right is actually 2 to the power of 0. This one is 2 to the power of 1. This is 2 to the power of 2, and so on and so forth. So really, this equates to 1. And by the way, anything to the power of 0 is 1. It's not times 0. So the power of 0, so that's 1. To the power of 1, that's essentially 1, 2. So we have 2, 4, just keep multiplying by 2. And there's your powers of 2. So this is what allows you to get those values that go from 0, which means no flags or no ones, all the way up to what's the biggest number? Come on, you've guessed it, 255. That would be if you put flags in every single one of these. All these are 1, and you added 128 plus 64 plus 32 and so on, all up. That would give you 255, which is the maximum value we can have for our IP address. So let's do one more, okay? Let's grab this 150. I'll use purple flags just so we can use the same diagram. So Rico again grabs his flag, says, okay, that's going to go in 128. So we have 150 minus 128. That'd be 5, 4, 10. That'd be 2, 222 left over. So no, no, yes. There's 1 in the 16. It'd be 2, actually 1 and 6, so 6 left over, right? And then we have flag here, there's our 6. So the binary equivalent of 150 is 1001. It's tough with the red flags. 1, 1, it's like a challenge course. That, as long as I've got my purple flags right, is the binary value of 150. Now, at any time, by the way, you can bust out the Windows calculator, flip on over to the scientific view. No, because this is Windows 7, and yes, we want the programmer view. So, it's gone. View programmer, and you can see that over here we have decimal and hexadecimal, binary, all those values. So I can come in here and say, well, what's 150 as a binary number, and that can confirm us. You can see 10, that's exactly what we drew up over there. So you can always check your work. Of course, the calculator is not available on an actual Cisco exam. So when we say 150, the computer says this, and that's the binary value. Okay. So with that skill mastered, and if you need some mastery of that, please take some time, run through a couple more examples, or go on Google, type in converting decimal to binary. I'm sure there's a million tutorials on how to do it. Let's now take that skill and talk about this subnetting scenario. We are the service provider, right? We are providing internet access. So we actually have uplinks to other carriers and all that kind of stuff out here. We'll call it the cloud, the internet. So we are an ISP delivering internet service down here to all these customers. So we have received a Class C network block of 205.11.2.0. So Class C, what does that tell us? Default subnet mask 255.255.255.0 that we have there, and we would like to evenly allocate that Class C subnet block between the customers shown. So I've got, let's see, 1, 2, 3, 4, 5, 6, 7, and I want to kind of divide out those IP addresses that way. Now, there's a problem with that, right? We have how many networks right here? How many, with what we have right here, how many networks do we have? 1. 205.11.2 based on our subnet mask. That is the only network that we have. So knowing that every interface of a router is a network, that leaves us with one customer taking all the addresses and us not being able to give it to them. Now, keep in mind, I'm trying to think how deep to get into the actual networking here. We can actually give these as the WAN link. We could say, okay, this will be the WAN link. This will address this network right here between us and the customer. Or we could actually slice this up and give it to them as individual blocks. So we'll have one subnet right here that we're not even talking about, and then they'll use these addresses maybe on a network behind this router or something to that effect. So those are all options that are there. Regardless, the result is the same. We want to take this and take one network and break it into 1, 2, 3, 4, 5, 6, 7 different networks. So here's the process. Step 1. Determine, and actually, hang on, let me pause it. I'll write it up and then I'll come back. Well, let me take this to a slide of its own. Over here, I've written the network that we have that we wanted to divide up evenly between our customers. Here's the process that we go through to do it. Number one, determine the number of networks that we want and convert it to binary. So we determined we had 7 customers. We wanted to divide this out evenly between them. So we want 7 networks when it's all said and done. How many does this give us right now? 1, 205, 11, 2. So I'm going to split this, or I guess split isn't the right word, break this into 7 individual networks. So we need to convert the number 7 to binary. 128, 64, 32, 16, 8, 4, 2, 1. There's Rico's palette sizes that he's using. So I'm going to look and quick and easy. No, 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 yes. So 7 minus 4 is 3. So yes, I can take a 2. That leaves me 1. So yes. So the binary equivalent of 7 is 0, 0, 0, 0, 0, 1, 1, 1. Right? Good. That's step 1. Step 2 is to reserve the bits in the subnet mask and find the increment. So we'll take this piece by piece. First off, reserving the bits in the subnet mask requires us to write the subnet mask in all binary. Now, someday you'll be able to gloss past this, but for now, do this every single time to make sure that you catch it. It's very easy to do because 255 is what in binary? All ones, right? So it's 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8 dot, and then 0 is all zeros. 1, 2, 3, 4, 5, 6, 7, 8, right? So hang with me for a second. I'm going to tie together a couple things. First off, looking at the subnet mask in binary, well, let me go back here. In decimal, what represents the network and what represents the host? Well, 255 represents the network. 0 represents the host, right? That's how when we line it up, we go, okay, this represents the network. But now I'm going to make the leap that says, okay, 1s in binary represent network bits, and 0s represent host bits, right? Not too big of a leap to make there. And oh yeah, that's right. So reserving the bits in the mask says, okay, I need to figure out how many more network bits I need in order to get 7 more networks. Now, I'm looking right here, and just from what I figured out, it takes 3 bits to get the number 7. I cannot, do you agree with me? I cannot, if I had 2 bits, what's the biggest number I could get? 3, right? A 1 and a 2, add those together if I put those both in 1. So I have to have 3 bits to get 7 networks. Well, this is what it looks like to reserve bits in the subnet mask. Is I say, okay, well, the network bits move along here, so I'm going to need 3 more. Yeah, I know. You're looking, you're like, okay, well, it's 0, 0, 0. This isn't all about taking this number and putting it down here. This is just about reserving and figuring out, okay, it takes 3 bits to get the number 7. That's all I care about from this number 1. They could be, 0, 1, 0, 1, 0, and I'd say, well, I'm just looking at how many bits did it take. Okay, so I'm going to take those bits, 3 bits, and go 1, 2, 3. 0, 0, 0, 0, 0. Now, why did I do that? Well, because in order to get 7 networks, right now we have 1 network, 205.11.2, and 254 usable hosts. And what I'm going to say is, no, I don't need 254 usable hosts. I need more networks. So I'm going to sacrifice these host bits. They're essentially gone. And replace them with network bits down here, which will give me enough network bits to reach the number 7. Right? I know, still a little fuzzy. If this is your first time seeing subnetting, it'll come together in just a little bit. And believe it or not, I already know what the subnet mask is going to be for my service provider network. All I need to do is convert this back to decimal. Well, all 1s we know is 255, so that's easy. Those just flip right back over to 255. Now, what about this one? How do we convert back to decimal? Rico didn't show us that. Well, we just line this back up to the binary chart, 1, 1, 1, 0, 0, 0, 0, 0, and we do simple math. We go, okay, there's 1, 128 plus 164 plus 132, carry the 1, 224. Right? You start getting used to seeing what values in binary give you what decimal value. So this is actually 224. So my subnet mask, my new subnet mask that I'm going to use in my entire service provider network is 255.255.255.224. Right? Okay. Now, that's the first path. Reserving the bits in the subnet mask. We now know what our subnet mask is, but it doesn't mean anything to us. So that's why I rely on the second part. Find your increment. Now, this is just going to be the rule, and I'll explain it more as we go. But the lowest network bit converted back to the decimal number is your increment. So looking at this, what is this value in decimal? Okay, right there. 32. That is your increment. That's what makes the subnet mask meaningful to you, because we look at this, we're like, woohoo, I got the subnet mask, you know, doing your little dance and all that kind of stuff, but it doesn't mean anything to us. We just say, well, that's the subnet mask. So we're going to take our network 205.11.2.0 and start adding our increment to it to figure out our network ranges. 205.11.2.32, 205.11.2.64. See what I'm doing here? I'm just adding 32, 96, 128, and down and down and down we go, right? Off the bottom of the screen. These all drop down as well. This is the start of each network range that we're going to give to our customer. Remember our network diagram. Here's us, the service provider, connecting to all these individual customers, and I want to be able to divvy it up. I want to be able to, say, okay, you get one equal share, you get one equal share. So I'm taking my Class C and dividing it amongst all these customers. So what ends up happening is these represent the start of each range that I'm going to give my customer. Now, to figure out the end range, I'm going to just do simple math. What's the last IP address before you get to 32? 31. I know some of you are like, is that a trick question? No. What's the last IP address, before you get to 64? 63. Just subtract 1. Minus, 95. And you just keep working your way down, 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 and down, and you go. This is network range number 1, essentially customer number 1, number 2, number 3. I can now divvy these out. This one goes here to this guy. This one goes here to this guy. So usable, let's talk usable. This customer is like, woohoo, I got a chunk of addresses from my provider. But remember, anytime we have networks, we cannot use the first nor the last address. So we actually usable by the customer have 1 through 30. That if they applied this, they would have that many usable addresses for their organization to have. This guy would have, again, 33 through 62. 31 represents the broadcast, 0 represents the network. Same thing here. 63 is the broadcast, 32 represents the network. So 30 usable hosts the whole way down. Good. Now, I know that's a lot more complex. I know some of you, if you think like me, you're probably like, okay, so I had 255 addresses and 7 customers, right? So let's just divide it. No, it just doesn't work that way. That's not how subnetting works. You have to go on binary boundaries, which is how the computer sees it. So when I take this 205, if I were to tell somebody, hey, I've got the address 205.11.2.0, and I'm combining that with the subnet mask 255.255.255.224. That changes the whole meaning. So when I give this to somebody, that immediately, if they know subnetting, is going to tell them, oh, okay, well, I only have 0 through 31 that's allocated to me. Now, they don't write it that way. They just look at it like this. However, that's what that subnet mask ends up meaning. Now, I realize walking through one subnetting scenario is not enough. Walking through 20 of them probably isn't enough. It takes a lot of practice. So I want to do more with you and hopefully fill in a lot of the gaps as we go and then release you to start practicing these on your own. So here's scenario number 2. I didn't want to draw this up because it just got too big. 195.520. This is the Class C network that we've started with, and we need to split this up into 50 networks. I know you're like, wow, this is big. It is. So what we're going to do is start the same way. 50 networks in binary. So I'll write up our binary chart. 128, 64, 32, 16, 8, 4, 2, 1. Right? Get that one committed to memory. So I'm going to look here. 50, that'd be none, none, 1. So 32, let's subtract 50 or 32 from 50. So it'd be 18. 16, that'd be 2 left over. So 0, 0, 2, 0, right? So our binary value for 50 is 00110010. Now, again, I want to make sure I emphasize that we're not necessarily after this binary number. We are after how many bits it took. So let me ask you, how many bits did it take to get the number 50? Now, some of you might be tempted to say, well, 3. Because I see 3 ones there, right? Well, I'm not talking 3 because 3 bits would be a maximum of 8, right? No, I'm looking at this and I'm saying, okay, I can't get the number 50 with any less than what? 6 bits, right? 6 bits. I need 6 bits. It doesn't really matter how many of them are 1 or not. The fact is I have to use 6 binary values, whether they're 1 or 0, to get this. And that's going to be key when we do this next step. So step number 2, reserve bits in the mask and find your increment. So 255, 255, 255. 0 was our original mask, so let's write it up. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8. Those are the host values. That's what we can play with because those are the ones that we really have. The rest, this network was given to us. We can't really change that. So what do I want? I want more hosts or I want more networks? I want networks. Right? So I'm going to look and I'm going to say, okay, I can't get the number 50. I can't get 50 networks when it's any less than 6 bits. I know that these network bits are ones. So I'm going to pick up from right where the ones leave off and go 1, 2, 3, 4, 5, 6, 0, 0. Now I know some of you might be like, whoa, 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 whoa. Your binary value wasn't all ones. It was 1, 1, 0, 0, 1, 0. Well, that's true. But again, we don't care about this. That's why I keep trying to emphasize it because it's easy to stumble over. Yeah, it's gone. We just want to know that 50 equals 6 bits, and we only have network or host bits. We don't have a blend in the middle of them both. So we're adding 6 network bits to our subnet mask, which results in a subnet mask of 255.255.255. Well, let's figure this last one out. We've got, well, there's a couple ways you can approach this. You can either say 128 plus 64 plus 32 plus 16 plus 8 plus 4, which is a nice big addition problem. Or you can know that we have 255 if all of these are ones, and you know that there is no 1 and there is no 2. So subtract 3, right? A little easier math to go that way. So we'll say 252. That's our subnet mask. I'm going to add one more piece in here. Okay? I told you I'm going to fill in a couple cracks as we go. This is becoming an old school way of writing the subnet mask. Now, I'm not saying it's immediate, like, poof, gone, nobody does it anymore. However, long ago, CIDR notation was created. It stands for classless interdomain routing. You've probably seen at some point like a /24 or a /16. What these are is shorthand. So for example, I could have written this same information here of class C address of doing 195.5.20.0/24. The slash number value thing, this thing right here is called CIDR notation, and it's representative of how many ones are in the subnet mask. Okay, so a class C network is 255, well, it's right there, 255, 255, 2550. Well, this is 8 ones, 8 ones, 8 ones. So add all those up, that's our 24 ones. So we could have written, instead of putting this here, I could have just put /24, and you need to be really familiar with both of them, I would say. But in a service provider environment, probably even more familiar with the CIDR notation. That's what's used all over the place. So we can write the subnet mask like this, or we could write it as a what? /30. Because we had our original 24 ones, right? And we added 6 more, so there are 30 ones, if you will, in the subnet mask. So that's our new custom mask. Okay, so that's all bonus information on reserving those bits in the subnet mask. Now let's find our increment. Lowest network bit converted back to a decimal number is 4. That's our golden value. Our increment that we're going to use to start finding these network ranges down here. So we'll take our class C address 195. Ooh, not writing it that. 5.5.20.0 is where we begin, and start adding the number 4 in the last octet there. So we'll have 195.5.20.4.8.12.16.20. Down we go. You can see a lot of networks, but very small, because when I fill in the end range, what's the last address before 4? 3, right? Fill in the end range, you see that right there. Initially, it's like, ooh, 4 addresses each. Nope, nope, nope. You can't use the first, you can't use the last. So what do we have usable? 2 addresses. Now I know. A lot of people look at that and go, well, that's crazy. What kind of nonsense is this? But we actually just found the second most popular subnet mask in the world, because this is the perfect subnet mask for WAN links, meaning links directly between routers. For instance, here's us as the service provider. Perhaps instead of giving the subnets we gave on the previous scenario here of 30 addresses, right? I was trying to remember 30 addresses, when really, just between these two routers, we're only going to use 2 of them. There's a lot of other ways that we can use 30 addresses, but for now, just go with me. So instead, what I could do is just chop up a public subnet and allocate 1 to each WAN link. So, 195.5.20.0/30 would go right here, which means maybe my side would be the .1, their side, the customer side, would be the .2. And then I'd go to the next range and say, okay, well, this one's 4 through 7, last address before 8, right? So usable, I actually have maybe my side be .5, and their side, the customer side, be .6. Again, that's the usable addresses inside of the unusable start and end of the range. You see what I mean there? So this is a really common subnet mask. You see it all over the place for WAN links. All right, let's go outside the Class C world into a Class B network, 150.5.0.0. And we need, in this case, 100 networks. So first step, convert the number of networks to binary, 128, 64, 32, 16, 8, 4, 2, 1. Now, just a word of a note as I'm thinking about this is we're not really after the binary number for 100, right? I mean, we are, but we're really after how many bits it takes to get that number, yeah? So when we're doing this, we may save a few seconds just by looking here and going, okay, there's no 128s. Oh, there's 164. Now, as soon as I find that first one where it's going to be, do I know how many bits it takes to get that number 100? I do. I know that I have to have 7 bits in order to get that number 100. I can't do it with any less. Now I could figure out the rest of this and figure out the whole binary equivalent, but it's all still going to come out to the same. I need 7 bits to get the number 100, and that saves us some time. So second step, and this is where it's even more critical to write things out in binary, we take our original subnet mask, 255.255.0.0, or would that be a /16 insider notation, equals 1, 2, 3, 4, 5, 6, 7, 8. Hey, there we go. I used the pause button and save some time. So we know that we need 7 bits to get the number 100, and we are trying to create more networks. It's kind of subnetting we're doing in this nugget. So I'm going to pick up right where the ones leave off. Don't make the mistake of going Class C. Right where the ones leave off. 1, 2, 3, 4, 5, 6, 7. 0 have been added on. 0, 0, 0, 0, 0 is the rest. So our new subnet mask is 255.255.254.0. We're in that third octet, or it would be a /23 subnet mask because there's 23 ones. I say, okay, what is my increment? Lowest network bit converted to a decimal is 2. Right? Now it does not, I know some of you might have been thinking, okay, 1, 2, 4, 8, and then so you keep going. We go, okay, 128, 256, 5, no. Every octet, it starts those increments over. So we're again back to 1, 2, 4, 8, that kind of thing. So we're at a 2. So now this is where it gets a little bit different. We go 150.5.0.0, but now we're adding in the third octet of the IP address. That's where the increment is. So we'll go 150.5.2.0, 4.0, and down and down and down we go. Fill in those pieces. And now the end ranges. This is where it's easy to get caught. We go, okay, what's the last possible IP address before 155.2.0? I'll show you. It's not 150.5.1.0, right? Because if this range ends at 1.0 and this starts at 2.0, then where is the IP address 150.5.1.50 per se? Just for example, it's lost. So the true last IP address before we get to 2.0 is actually 1.255. Right? And this one goes through 150.5.1, hold the phone, 3.255. The last one before 4. And this, you see the pattern now, 5.255. And this would be, 7.255. And we just keep going down. Now, in these ranges, first off, which are larger, how could I figure out how many hosts? Well, that's where I could use the 2 to the power of value. 2 to the power of whatever number of host bits I have. So in this case, I have 8 host bits here and one more. So that'd be 9. 2 to the power of 9 will tell me exactly how many hosts. Subtract 2. Why do I subtract 2? Because I can't use the first or the last. So truth be, I mean, you can pull out a calculator and do that. Let me show you how to do it on a calculator. And then I'll show you how to do it. I don't know. I'm so used to opening a command prompt. So I'm going to go, let's go back to the standard. 2 to the, never mind. Let's go back to the scientific. Okay, there we go. 2 to the power of 9 equals, and there's my 512. So 512 minus 2, 512 minus 2 equals 510 usable host addresses in there. Now, if you didn't have a calculator like you were on a Cisco exam, well, you can remember that these are the powers of 2, starting from 2 to the power of 0. So this is 2 to the power of 1, 2, 3, 4, 5, 6, 7. So we go, okay, I need 2 to the power of 9. So you could just say, okay, 8 and 9. So I could just multiply this by 2, 256, 512. Save some math. Again, it's finding powers of 2 by hand is never fun. And so Cisco is not going to ask you for something crazy big, but they might ask you for something like this because they want to know that you know These are the powers of 2. Other thing that I want to mention here is that in this range, you're going to run across the IP address 150.5. They'll say 1.0, right? Can you use that? And could I actually assign that to a PC or a router or some device? Yeah, I could. Because in these ranges, I mean, there's only one start and only one end address. Now, it's going to feel weird because we're so used to using Class C subnet masks that using anything with 0 or 255, as a matter of fact, in that range, right next to this one is going to be 150.5.0.255. Again, can I use that? Yeah, it's right in the middle of the range. It's just, this is my network, this is my broadcast. We're just not used to using an address like that, but it works just fine. And that same thing happens the whole way down. Can you see the kind of question that Cisco could ask you on the exam? Which of the following addresses are valid given this subnet mask and so on and so forth? So we can look at this and say, oh, okay, well, only one start and only one end of each range. Everything in that squishy Oreo center is good. All right, last one that we're going to do here is going to be a Class A network, and I'm shocked they need 1,000 networks. Again, thinking from the service provider mindset, we're now thinking, okay, we've got large address blocks that we're dealing with, and we need to divide it up for a large gamut of different customers. So now, one thing I'll save the commentary. Let's figure this one out first. We've got 1,000 networks. We've got 128, 64, 32, 16, 8, 4, 2, 1. And don't worry, that commentary is going to be coming. It just comes at the end. Okay, that's a problem. 1,000 networks. It doesn't fit. We can only get 255 in our 8 bits. So what do we have to do? Go further. 256. Well, essentially, I'm going as far as I need to make sure that I can get the number. I'm just multiplying by 2 so I can get the number 1,000. 20. Actually, I don't have to go any further. So what's where does the first 1 go? How about that when we're converting from binary? It doesn't go right here, right? We can't take away 1,024 from 1,000. It goes right here. So we immediately know, and again, we could figure this out the rest of the way, some long number, but we now know it's going to take how many bits to get the number 1,000? Well, here's our 8 bits, 9, 10. So 10 bits to get the number 1,000. Okay. Now we need to reserve the bits in the subnet mask. So our original subnet mask is 255.0.0.0, that Class A network this time. So I'll put equals this big long binary number, right? So we've got 8 ones, that's the network bits, followed by 24 host bits, so a ton of host bits that we can play with. And now we need to reserve those bits. So I need 10 network bits. Pick up where the ones leave off. 1, 2, 3, 4, 5, 6, 7, 8. Dot 9, 10. 0, 0, 0, 0. So all the rest remain 0, right? So, et cetera, et cetera. So our new subnet mask goes to 255.255. And what's this one? 128 plus 64, 192.0, or CIDR notation /18, right? So we got 16 ones plus 2 more. Our increment, let's flip over to the purple color, lowest network bit back in decimal, so 128.64 is our increment, right? Good. So use our increment to find our network ranges. So we've got 10 is our base address. Now, it's pretty rare, unless you are using private addresses like this, that you would be able to start with a Class A public subnet. They just don't exist anymore that are not being used. Everybody's chopped those things up a lot. But let's say we had one, or we're doing the 10 network. So we'll do 10.64.0.0, right? Because wrong. We're in the third octet. So 10.0.64.0. 10.0.128.0. Now, hang on, I want to take this one a little further. What happens here? 192.0. 10.0. What happens when you add 64 to 192? 192, 64, be 6, 5, carry the 1, it'd be 2. 250. No. You can't. Sorry, you can't have 256. What does this mean? Is it broken? What does that mean? Well, all that means is you've reached the end of that octet. So I would say, okay, well, let's just for example, let's fill in the end ranges. This goes through 10.0.63, 3.255. Then put the dash. This goes through 10.0.127.255. Now, how about this one? 10.0.191.255. Now, what about this? If we add that 64 and this goes to 256, what does the end go to here? It just goes 10.0.256. 255.255 would be the last IP address before you got to that 256 there, right? So now are we done? No, no, no. We've got, how many subnets do we have? Well, we've got 10 bits worth of them. I mean, we could, keep going with this entire octet. So the next one just, if we were to do a +1, the next one would start at 10.1.0.0. So again, the pattern starts going from there, 10.1.64.0. Do you see, it's kind of how we made that jump from one to the other. So anytime you see that 256 when we're adding, it either means you're done, like if you didn't have these subnet bits, or it's time to increment the next octet and just keep going down the range. Now, what I was going to comment on from the very beginning is these subnets are very big. I mean, if you look, we've got 8, 9, 10, 11, 12, 13, 14 host bits that are available. Just do some quick math on that. Wait a sec. 2 to the power of 14 is 16,000. Now, not good practice to have a network with 16,000 devices on it. So what would probably happen is we would give these, like for instance, I would say, okay, let's assign that to a network. Some network, maybe this is our Arizona region, right, where we have a gamut of offices. Hey, you guys get 10.0.0.0, and this is how you write this, by the way, /18. Which then implies, and by the way, I don't usually write it like that because I can't do that in my head. I'll usually write this. Now, this is not standardized, but this is what I do when I notate things on documentation. I say, okay, Arizona is actually 10.0 through 63.0/18. So that way I can look real quick and go, oh, okay, that's a big block. Don't put that on an exam or anything like that. That's just how I write them, so I don't have to reverse engineer these, which by the way is going to be in a future nugget on reverse engineering them. But then once I get to Arizona, I would subnet the subnet. I would then break that down further and say, okay, well, that'll be our starting point essentially for step 2, and I need to break that now into maybe the 15 offices that I have in Arizona, or the 20 offices, or whatever I have for that, because those subnets are very large. Now, I've seen it happen a million times. People go through these lectures with me, and they're like, oh, this is great. I get subnetting. I'm so excited. And then they get home, and they forget it, because it's one of those skills you just won't remember unless you do it a number of times yourself. I've included some homework for you on the screen. I know, homework. I mean, don't think of it as homework. Just do it right now. I mean, pause the video, work through each one of these on your own right now. Now, in the course download files, I actually have the answers to these. So I've not only written the answers, but actually done the step-by-step on paper for you, so you can actually go and verify your work. Please go through these. Please, when you're done with these, then go out online and just search the web for subnetting practice, and you'll find 1,000 websites that have sample problems like this, or just again more and more. Now, coming up, I've got 2 more nuggets on subnetting, 2 or 3. Where we're going to get into some different styles of subnetting. So you will get more practice in the series, but take some time right now. Go ahead and do this on your own. So with that, we'll wrap up Subnetting Style 1, which is simple subnetting based on network requirements. In the next nugget, we'll change the name of the game and actually go with based on host requirements. But for now, I hope this has been informative for you, and I'd like to thank you for viewing.